Students, the next topic is density of states in quantum wire. Quantum wire is a one-dimension particle, which means the motion of the electron is allowed only in one direction, which means it's only one dimension is in the normal scale and other two dimension are in the nanoscale. That is called as a quantum wire. So consider the one-dimension system, the quantum wire, in which only one direction of motion is allowed. Say for example, x-axis is in the normal scale, normal dimension, and the y and z are in the nanoscale, right? In one dimension, such as the quantum wire, we are saying as a one dimension means we take example as quantum wire. The density of energy state is the number of available energy state per unit length. For the one dimension, we are saying as the length, and for the two dimension, that is quantum well, we are saying as a circle, and for three dimension, we already know it's a bulk material, right? So per unit length per unit area around the energy E. So we already know this limitation at x is equal to 0, the potential energy is 0, that is the electron inside the wire is 0 and outside the wire is infinity, right? At the point of, at the end of the A, and the end of A, the potential energy is infinity and the electron outside the wire is infinity. We all know the conditions from the unit 1. So we can write the radius as n squared is equal to nx squared. Therefore, the number of energy state lying in the interval of length, outer length minus inner length. So n plus dn minus n, we get dn. The difference in length is dn. From the Schrödinger eigenvalue, E is equal to n squared h squared by 8m a squared. And our rearranges equation, n is equal to 8m star. We are changing this m into m star. We know m star means effective mass of the particle. When the electrons are moving the higher energy level, we are saying as effective mass of the particle. So 8m star a square E by h square whole per half, and E is a variable, remaining everything is a constant. So we're taking outside. So 8m star by h square whole per half a into E per half. This is the equation of n. So we want to differentiate the E, so that we are getting dn is equal to, this is a constant. So 8m star by h square whole per half, and a differentiating E, we get half into e per minus half into dE. Substituting this equation dn in this equation, we get n of e d is equal to 8m star per h square whole per half. The same equation, a half e per minus half into dE. So this is the equation for the energy level. We know as per Pauli's exclusive principle, in each energy level 2 electrons can occupy, and the number of energy level per unit length means we want to divide this A, right? So therefore n of e dE, which is nothing but density of states. Density of states per unit length is nothing but, so we getting this, dividing this equation by A cancel, therefore we get 8m star by the h squared will be changed into 2 pi h bar square. We already see it in the quantum well, right? Already see the quantum well. So 8m star by 2 pi h bar square into e power half. In the case of quantum well, we don't have any e term, that is 0. Okay, that is a constant. Is a constant. We have only the constant term. E is not available. But here we have the e term, energy term. Therefore, how we can write density of state? That is density of state in one dimension is equal to, rearrange this equation. We get 1 by pi h bar root of 2m star by E minus E naught, where for the E is greater than or equal to E naught, where E naught is a ground state. So what we are saying, for the only one energy level, it is E per half, e power minus half. It is actually e per minus half. But for the more than e per minus half, for if we have more than one energy level, example semiconductor, that is, see, it has functional dependence of energy for more than one state is given by, if we have more than energy level, more than one energy level, we can write as z of E one dimension is equal to 1 by pi h bar summation of energy levels. How many energy levels? We can say n. Therefore we get root of 2m star by E minus En into the constant sigma E minus En, right? Where sigma is a constant function constant, the waveform is in this formation. There is a graph between the E and the z of E. This is a particle. This is a one dimension particle, and the waveform will be in this form. Next we go to the 0 dimension. Density of states in 0 dimension, that is called as quantum dot. See, Here the movement of the particle, movement of the electron is confined in all the three dimensions. Hence the motion of the electron is not possible. When all the size are reduced to nanoscale, the movement of electron is confined. Since it cannot move, that is called as the no motion of electron is possible. That is called quantum dot zero dimension particle. So we have only one energy level, and in this we have two electrons, right? So for the so each state of energy level is occupied by two electrons. So the density of state in the delta function can be written as Z of zero dimension is equal to 2, for which represent two in each energy level two electrons can occupy, and root of E we are getting from the bulk materials. Root of E, can you remember this E per half? So root of E, for if we have so two or three more energy levels, we change this equation into E minus En. Okay, so for more than one quantum state, how we can write? Z of E zero dimension, which is equal to summation of n into 2 delta root of E minus En. This is a graph for the, there's a value between E and Z of E. The waveform will be in this formation.